0.12 to 2.13. 2007. A single millisecond radio pulse explodes from the darkness, so powerful it does not belong anywhere near our galaxy. Was it a glitch, a celestial accident, or a signal from deeper in the universe than anything ever measured? Astronomers scramble to make sense of its impossible strength, its echo traveling farther than any known radio burst. If the secrets behind this origin story are real, every map of the cosmos could be wrong. Today, we journey through evidence that challenges everything. Prepare yourselves. We begin. Duncan Lorimer sat hunched over a mountain of archival data from the park's radio telescope, chasing a hunch that something extraordinary might be hiding in the noise. He was not searching for a specific signal, just the faintest sign of something unexpected. In 2007, his patience paid off. Buried in the records was a single, isolated radio pulse. It lasted less than 5 milliseconds, yet its intensity was off the charts. The numbers did not add up. The burst's fluence, a measure of its total energy, dwarfed anything seen before. This was not a routine blip or a known cosmic phenomenon. It was a spike so powerful that, if it were local, it would have fried every instrument at Parkes. But the signal was clean, no interference, no known satellite, nothing that could be traced to human origin. Lorimer's team ran through every possible explanation. Terrestrial interference was ruled out, an instrumental glitch was considered, but the data held up under scrutiny. The bursts sweep across frequencies, the telltale delay of lower radio waves arriving after higher ones, hinted at a journey through vast stretches of ionized space. That sweep, called dispersion, usually reveals how far a signal has traveled. But this burst's dispersion was so extreme, it suggested a source far outside the Milky Way, perhaps billions of light years away. Yet the sheer strength of the pulse defied easy answers. The Parkes telescope had been scanning the sky for years, but nothing in its archives looked remotely like this. As news of the discovery spread, astronomers around the world began combing through their own data, searching for similar events. The question was no longer whether the burst was real, but what kind of cosmic engine could unleash such a brief, brilliant flash? Lorimer's impossible click had cracked open a mystery that would haunt radio astronomy for years to come. The need for a new way to measure cosmic distances became urgent. The search for an explanation had begun, and the rules of the game had already changed. Radio astronomers needed a way to turn the sweep of a burst into a ruler for the cosmos. That ruler is called the dispersion measure, dm. It is a single number, but it carries the weight of the universe's invisible matter. The dispersion measure is measured in units of parsecs per cubic centimeter. It counts how many free electrons, on average, a radio wave encounters along its journey from the source to Earth. The higher the dispersion measure, the thicker the cosmic fog the signal has traveled through. When a radio burst races through space, it does not travel at the same speed across all frequencies. Higher frequency waves arrive first. Lower frequencies, slowed by the sea of electrons in space, lag behind. This frequency-dependent delay follows a precise mathematical relationship. The dispersion measure links the arrival time difference between frequencies to the total column of electrons along the line of sight. In practice, astronomers plot the burst's arrival times across different frequencies. The result is a sweep, a sloping line on a waterfall plot. The steeper the slope, the more electrons the signal has crossed, and the greater the dispersion measure. A dispersion measure above 100 parsecs per cubic centimeter already hints at a source far outside our solar system. Values above 300, 500, or even 1,000 push the possible origin to intergalactic distances, hundreds of millions or even billions of light years away. For the Lorimer Burst, the measured dispersion measure was so high it ruled out any local source. The signal had to have crossed vast stretches of plasma, likely traveling from another galaxy altogether. The implication was extragalactic and profound. This single number, distilled from the radio fog, connects a fleeting millisecond pulse to the scale of the universe. The dispersion measure does not just tell astronomers how far, it hints at what lies between: clouds of gas, the halos of galaxies, the deep intergalactic medium. Every new burst, every new dispersion measure offers a new probe of the universe's hidden structure. With the dispersion measure as their guide, astronomers could begin to map the cosmic distances of these mysterious signals, one sweep at a time. Milliseconds matter in the world of fast radio bursts. Each one is a fingerprint, an intricate pattern of spikes and subbursts packed into a blink of cosmic static. For years, these fingerprints seemed random and impossible to predict, as if the universe were tossing out radio pulses with no rhyme or reason. That changed in 2020 when the Canadian Hydrogen Intensity Mapping Experiment, called CHIME, caught something no one expected: a repeating burst, not just in its recurrence, but in its timing. The source, cataloged as FRB 180916.J0158+65, did not just fire off bursts at random intervals. It kept a schedule. CHIME data revealed a clockwork pattern, a cycle lasting 16.35 days. For about 4 days in each cycle, the source became active, firing off bursts in rapid succession. Then, like a lighthouse beam swinging away, it went silent for the next 12 days. This was not a fluke. Over dozens of cycles the pattern held, as regular as the phases of the moon. The bursts themselves were no less remarkable. Some lasted less than a millisecond, packed with fine structure, multiple peaks, sharp rises and falls, and in rare cases, subbursts separated by mere fractions of a millisecond. The shortest structures resolved by CHIME were as brief as 0.3 milliseconds, hinting at an engine smaller than a planet, maybe even smaller than a city. Statistical analysis of FRB 180916 activity windows showed a clear duty cycle. About 24% of each 16.35-day period was active. During those windows, bursts sometimes arrived in clusters, separated by minutes or hours, but never outside the predicted on phase. The periodicity was so precise that astronomers could predict almost to the day when the next burst would come. This kind of regularity challenged the idea that all fast radio bursts are the signatures of one-off cataclysms, supernova, neutron star collisions, or black hole mergers. Whatever was happening here, it was repeating, and it was following a schedule dictated by some underlying clock. The implications ran deep. Millisecond scale structure meant the emission region had to be incredibly compact, no larger than a few hundred kilometers across. The strict periodicity suggested an orbital or rotational mechanism, perhaps a neutron star in a binary system, or a precessing magnetar whose beam swept past Earth on a fixed schedule. The pattern of activity and silence hinted at environmental factors, maybe a companion star, or a disk of material periodically blocking or enabling the bursts. What set FRB 180916 apart from earlier discoveries was not just its repetition, but its predictability. Most fast radio bursts are one-hit wonders, never seen again. Even among repeaters, none had shown such a crisp periodic window of activity. This regularity allowed astronomers to plan targeted observations, catching bursts in the act and studying their detailed structure with unprecedented clarity. The CHIME team findings, published in Nature in early 2020, forced a re-evaluation of fast radio burst models. The universe, it seemed, was not just throwing out random flashes. In at least one case, it was keeping time. The search for answers now turns to the environment of FRB 180916. What could cause such a precise rhythm? And what exactly is happening during those brief, furious windows of activity? Magnetism leaves a signature even when the engine itself is hidden. After the first repeating fast radio bursts, astronomers turned to a new kind of cosmic fingerprint called the rotation measure, called RM. Rotation measure quantifies how much a radio wave's polarization angle twists as it travels through a magnetized plasma. The stronger the magnetic field and the denser the electrons along the path, the more the polarization rotates. It is measured in radians per square meter, and it is a direct probe of the magnetic chaos around a burst's origin. The numbers that came back from some repeaters were staggering. In 2018, a team led by Chiara Micili measured the rotation measure for FRB 121102, the first known repeating source. The result was nearly 100,000 radians per square meter. That is not just high, it is among the most extreme values ever recorded in astrophysics. For perspective, the Crab Nebula, one of the most famous supernova remnants in our galaxy, has a rotation measure of just a few hundred radians per square meter. Even the center of the Milky Way rarely exceeds a few thousand. A rotation measure of 100,000 means the burst's radio waves spun through a magnetic gauntlet, twisting thousands of times before reaching Earth. The physics behind this is called Faraday rotation. As a linearly polarized radio wave travels through a region filled with free electrons and magnetic fields, its polarization angle rotates. The amount of rotation depends on the strength of the magnetic field along the line of sight and the density of electrons. The rotation measure is the sum total of this twisting integrated over the entire journey from source to observer. In practice, astronomers measure how the polarization angle changes with frequency, and then extract the rotation measure from the slope. Such a colossal rotation measure can only come from an environment where magnetic fields are both strong and tangled, and where electrons are packed densely enough to matter. The implication is clear. FRB 121102 is not sitting in the outskirts of a quiet galaxy. It is embedded in a region of violent magnetism, possibly near a young supernova remnant, a pulsar wind nebula, or even the accretion disk of a massive black hole. The environment is so extreme that it rivals or exceeds those found near the center of our own galaxy, where magnetic fields twist and snap with relentless force. What is more, the rotation measure of FRB 121102 has not stayed constant. Over months and years, it changed by tens of %, suggesting that the magnetic environment itself is shifting, expanding, cooling, or being reshaped by winds and shocks. This kind of variability rules out distant uniform sources of rotation like the intergalactic medium. The twisting must be happening close to the source, in a region dense and dynamic enough to evolve on human timescales. Other repeating fast radio bursts have shown similar, though sometimes less dramatic, rotation measures. Each new measurement adds texture to the picture. Some bursts pass through relatively quiet environments, while others bear the unmistakable scars of magnetic violence. The rotation measure, alongside the dispersion measure which tracks free electrons along the path, gives astronomers a two-dimensional map, one axis for how far, another for how furious the magnetic storms along the way. These magnetic fingerprints do not just hint at the violence of the source, they demand it. To twist radio waves by 100,000 radians per square meter, nature must marshal fields and densities far beyond what is typical in the galaxy. The evidence points to a birthplace steeped in magnetism, where the rules of ordinary astrophysics bend and sometimes break. Within these habitats, fast radio bursts are not just signals, they are survivors, carrying the imprint of every magnetic storm they have crossed. ASCAP, the Australian Square Kilometre Array Pathfinder, changed the search for fast radio bursts by catching them as they happened and tracing their origins to specific galaxies. Before ASCAP, FRBs were little more than fleeting signals, their locations smeared across the sky. ASCAP's rapid response system could pin down a burst to within a few arc seconds. In 2018, it directly linked a one-off FRB to a host galaxy, ending years of speculation about whether these bursts came from galactic outskirts or the vast emptiness between galaxies. A turning point came with the discovery of persistent radio sources tied to some repeating FRBs. FRB 121102, the first of its kind, sits atop a compact, steady radio glow so small that even the sharpest VLBI arrays cannot resolve it. The source is less than a parsec across. A parsec is about 3.26 light-years, smaller than the distance from the Sun to the nearest star. This glow does not flicker with each burst. It remains constant year after year, while hundreds of millisecond bursts erupt from the same spot. The evidence points to a dense, energetic environment, perhaps a young magnetar shrouded in a nebula or the remains of a recent supernova. Yet the persistent source and the bursts seem to operate independently, sharing a location but not a rhythm. FRB 20190520b, discovered by the FAST telescope and localized by the VLA, added another layer. It repeats and is anchored to a persistent radio source in a dwarf galaxy at redshift 0.241. a galaxy where star formation is rampant and massive stars live fast and die young. The persistent emission is again compact and steady, clearly decoupled from the bursts themselves. These repeating FRBs with persistent sources often appear in small, active galaxies, though other repeaters show up in larger, quieter hosts as well. Localization has also revealed the turbulent paths these bursts travel. As an FRB's radio pulse crosses the cosmos, it weaves through clouds of ionized gas, star-forming regions, and the diffuse plasma between galaxies. Each layer leaves its own mark, scattering, smearing, or even splitting the pulse into echoes. Some bursts show signs of extreme turbulence in their immediate surroundings, with scattering tails and scintillation patterns that betray dense, clumpy plasma. Others travel cleaner routes, hinting at calmer environments. The most profound insight comes from counting how much matter these pulses encounter. Jean-Pierre Macquart and colleagues analyzed dozens of localized FRBs, measuring their dispersion, the frequency-dependent delay caused by free electrons, and subtracting the known effects of the Milky Way and the host galaxy. What remained was the signature of the intergalactic medium, the thin gas that fills the space between galaxies. By comparing the observed dispersion to the distances of the host galaxies, Macquart's team solved a long-standing puzzle: the location of the universe's missing baryons. Baryons meaning ordinary matter made of protons and neutrons. The numbers matched. The intergalactic medium holds just the right amount of ordinary matter to account for the cosmic census. Each FRB acts as a cosmic yardstick, measuring the density of invisible gas across billions of light years. Thousands of FRBs likely occur every day, each lasting less than a blink. VLBI observations show the sources are tiny, less than a light day across, sometimes just a few thousand kilometers. The energy released in a single burst can rival the sun's output over decades. The persistent sources anchor these bursts in space, but the journey each signal takes reveals the hidden highways of the universe. On April 28, 2020, an ordinary patch of the Milky Way lit up with a burst of radio energy unlike anything seen before. The signal lasted just a fraction of a second, but its intensity was unmistakable. Astronomers traced the flash to a known magnetar, SGR 1935 + 2154, located around 9 kiloparsecs from Earth, deep in the constellation Vulpecula. For years, magnetars had been prime suspects in the hunt for the engines behind fast radio bursts. All the evidence had been indirect, drawn from galaxies far beyond our own. This time, the culprit was nearby and close enough to study in detail. STARE-2, a radio array built from repurposed satellite dishes and designed for speed rather than sensitivity, provided the crucial detection. STARE-2's true strength is its ability to catch rare, bright flashes that other instruments might miss. On that April morning, STARE-2 recorded a fluence, total received energy, of about 1.5 megajansky milliseconds, a value so high that it rivaled the brightest radio signals ever detected from within our galaxy. But the real shock came when astronomers compared this galactic flash to the weakest fast radio bursts ever seen from other galaxies. Despite SGR 1935 + 2154 being thousands of times closer, its burst was only about 30 times less energetic than the faintest extragalactic FRBs. The numbers forced a rethink. If a magnetar in the Milky Way could produce a burst this powerful, why are similar events not being detected all the time? And if extragalactic fast radio bursts are truly that much brighter, what makes those distant engines so much more extreme? The timing of the event added another layer. The radio flash coincided almost perfectly with an X-ray burst from the same magnetar, observed by multiple space telescopes monitoring the region. This multi-wavelength match rules out coincidence and points squarely at a connection between magnetar flares and fast radio bursts. For the first time, astronomers have proof that at least some fast radio bursts can be powered by the violent magnetic tantrums of a neutron star. Yet the comparison raises a stubborn paradox. If the burst from SGR 1935 + 2154 is typical of what magnetars can do, why are most fast radio bursts detected from galaxies millions or billions of light years away so much brighter? The energy gap is too large to ignore. Some theorists propose that distant magnetars must unleash even more powerful flares. Others argue that beaming narrow jets of energy pointed directly at Earth can make distant bursts appear brighter than they really are. There is also the possibility that rare conditions or exotic environments amplify the signal, making some bursts stand out from the cosmic background. The STAR-2 detection does not solve the fast radio burst mystery, but it changes the rules. It proves that magnetars can, under the right circumstances, produce radio flashes that echo across the galaxy and beyond. It also exposes a new challenge, reconciling the modest energy of our local magnetar with the blinding brilliance of its extragalactic cousins. As astronomers pore over the data, the debate over energy, beaming, and the true nature of fast radio bursts only deepens. The paradox has moved from possibility to center stage, and the search for answers will push the boundaries of both observation and theory. The discovery transformed a speculative idea into testable science. It opened new questions, and it set the scene for a deeper investigation into how magnetars behave and how the universe produces flashes that can be seen across vast distances. Prepare yourselves. We begin. The gap between a modest galactic magnetar burst and the searing brilliance of extragalactic fast radio bursts has become a battleground for competing ideas. Some researchers argue that the answer lies not in the raw power of the engine, but in how that energy is delivered to Earth. The concept of beaming takes center stage. If a burst is funneled into a narrow jet and Earth happens to lie in its crosshairs, the apparent brightness can soar, amplified by factors of 10, 100, or even more. Relativistic beaming makes this possible. When plasma is hurled outward at speeds close to the speed of light, with Lorentz factor gamma around 100, the observed intensity can be boosted by gamma to the third power or gamma to the fourth power, depending on the emission process. In plain terms, a burst that seems ordinary from the side could look blindingly bright if seen head-on. Others point to the role of plasma lensing, where clouds of ionized gas act like cosmic magnifying glasses. As a radio pulse passes through these caustics, its intensity can spike, sometimes by a factor of a few, as the waves are focused along certain lines of sight. But lensing alone rarely explains a factor of 30 in energy between the brightest galactic bursts and the faintest extragalactic bursts. The numbers suggest lensing may play a supporting role, but not the lead. Bing Zhang, a leading theorist, has argued for a more nuanced picture. In his view, both beaming and intrinsic diversity in burst mechanisms must be considered. Some magnetar flares might launch tightly collimated jets, while others radiate more broadly. The local environment, magnetic fields, plasma density, even the presence of a companion star could further shape the outcome. Zhang emphasizes that the diversity of observed fast radio bursts, from one-off flashes to clockwork repeaters, hints at a spectrum of engines and emission geometries, not a single universal recipe. Testing these ideas requires careful attention to observable signatures. If beaming is responsible, we should see strong polarization in the radio waves, and perhaps a preference for certain viewing angles. Doppler boosting would affect not just the brightness, but the spectrum and the temporal structure of the bursts. Plasma lensing would produce characteristic patterns, frequency-dependent amplification, echoes, or even multiple images of the same burst separated in time. Future observations will need to track not just the energy of bursts, but their polarization, spectral evolution, and arrival time structure. Statistical studies comparing the rates of bright versus faint bursts, or the distribution of fluences across the sky, can reveal whether beaming dominates, or if a true range of intrinsic powers exists. Each hypothesis makes predictions that can be tested as new data pours in from CHIME, FAST, and next-generation arrays. For now, the field remains open. The beaming model offers a way to reconcile the energy gap, but it demands extreme alignment and high Lorentz factors. Plasma lensing explains some but not all of the amplification. A mix of mechanisms shaped by local environment and cosmic geometry may ultimately be at play. The challenge is clear. Only by collecting and analyzing a vast array of bursts, dissecting their polarization, spectra, and arrival time structure in fine detail, can astronomers hope to bridge the gap between what we see in our own galaxy and the fireworks lighting up the distant universe. A new generation of radio telescopes is transforming the search for fast radio bursts. The Square Kilometer Array, or SKA, represents the most ambitious leap yet. When completed, SK will combine thousands of antennas spread across continents, forming a virtual dish with a collecting area of 1 square kilometer. This scale gives SKA the sensitivity to detect radio flashes 10 times fainter than any current instrument, and its array design allows it to pinpoint burst locations to within a fraction of an arc second, less than the width of a human hair seen from 1 kilometer away. SKA's survey speed means it can scan vast swaths of the sky in real time, catching fleeting bursts that earlier telescopes would have missed entirely. MeerKAT, already operational in South Africa, is a powerful pathfinder for SKA. With 64 dishes arranged in the Karoo Desert, MeerKAT combines high sensitivity with flexible observing modes. It can track known repeaters with split-second timing or sweep the sky for new, undiscovered transients. MeerKAT's precise localization capability has already tied FRBs to their host galaxies, narrowing the search for their origins. Its ability to record bursts with fine frequency and time resolution lets astronomers dissect each event in detail, revealing subtle structures hidden in the radio noise. In China, the 500-meter aperture spherical radio telescope, FAST, pushes the limits of single-dish sensitivity. FAST's massive dish, the largest in the world, can detect radio flashes with fluence as low as a few milliseconds, opening a window onto the faintest, most distant bursts. Its high sensitivity has made FAST a leader in discovering new repeating FRBs, and its polarimetric capabilities provide crucial data on the magnetic environments of these sources. FAST's pinpoint localization, often within a few arc seconds, allows rapid follow-up with other telescopes across the electromagnetic spectrum. These instruments are not just more powerful, they are fundamentally changing what is possible. SKA's immense collecting area and interferometric precision promise to uncover thousands of bursts each year, with positions accurate enough to tie them to individual star-forming regions or even to specific supernova remnants. MeerKAT's flexible scheduling and rapid data processing mean that no burst goes unnoticed, while fast sensitivity brings the faintest signals into view. Together, these radio eyes are turning the once rare phenomenon of fast radio bursts into a routine part of the cosmic landscape. The next step is to combine their discoveries across wavelengths and across continents to test the deepest laws of physics and probe the universe in ways never before imagined. A fast radio burst is more than a fleeting cosmic signal. It is a challenge thrown at the universe's most fundamental laws. When one erupts, astronomers do not just note its arrival, they break down its fingerprint across the spectrum, searching for the smallest cracks in physics. Every millisecond of delay between frequencies, every subtle shift in timing becomes a tool for testing the rules that govern reality. Optical follow-up is essential. As soon as a burst is caught, telescopes worldwide turn to the same patch of sky, capturing light from visible to gamma rays. These observations go beyond pinpointing a host galaxy or measuring distance. They let scientists compare the arrival times of photons at different energies, hunting for the faintest lag. If photons of different colors arrived at different moments, not because of plasma along the way, but because the speed of light itself varied, it would overturn Lorentz invariance, a foundation of Einstein's relativity. Fast radio bursts have become some of the sharpest tools for this job. Their timing is astonishing. For certain bursts, the difference in arrival times between radio and optical photons is less than 1,000th of a second, even after traveling billions of years. This level of precision sets strict boundaries on how much the laws of physics could possibly bend. The tightest limits on Lorentz invariance violation now come from measurements of fast radio bursts, with photon speed differences constrained to less than 1 part in 10 to the 20th power. If photons of different energies traveled at even slightly different speeds, these bursts would reveal it. The same data probe another question: do photons have mass? In theory, photons are massless, but if they had even the tiniest mass, lower frequency radio waves would lag behind higher frequency ones, not just from plasma but from their own inertia. Fast radio bursts with their broad frequency sweeps and crisp arrival times are the perfect laboratory. Recent studies have pushed the upper limit on photon mass below 10 to the minus 54 kilograms, a number so tiny that it would take over 1,000,000 times the mass of an electron to equal a single grain of sand. These are not just numbers. They reach into the core of quantum field theory and relativity. Each new burst is a fresh test. As tools sharpen, radio arrays, optical telescopes, and gravitational wave detectors put the universe under ever more precise scrutiny. Fast radio bursts now stand as precision probes, measuring the fabric of reality with every sweep across the sky. Vera Rubin's work comes to mind, a scientist who, by charting galaxy rotations, forced the world to confront dark matter. Today, fast radio bursts serve a similar purpose. Where Rubin used optical spectra to reveal the invisible, astronomers now use radio bursts to probe the hidden rules of space and time. The universe has yet to yield a violation, but with each burst, the search presses on. Right now, more than 80% of our universe is made up of vast, silent voids, shaping the cosmic web and influencing every galaxy's fate. As next-generation telescopes come online, each new discovery redraws the boundaries of what we think is possible. Our place in the universe is not at the center, but at the edge of mystery. The void reminds us, emptiness is never empty. Share your thoughts on what lies beyond.